Hello students. So let's try to solve one problem from Jest 2021 examination. And this problem is from small oscillation. And this is this is question number 14, part B of the set T. So you can just check what is the actual problem, but I will also explain it. So in this problem, what is given? There are two blocks, A and B. A is constrained to move along x-axis and B is constrained to move along y-axis. And from the origin, both the particle is attached with the spring, and this spring is massless, but its natural length is L and L, as well as its spring constant is K and K. But also these two blocks are interconnected with another spring, whose natural length is √2L and a spring constant is K dash. So what we have to do, we have to just calculate the basically normal frequency of the oscillation. So to calculate the normal frequency of oscillation, first we have to write the kinetic energy of a system, then we have to go for potential energy of a system, then we can use the matrix method to solve it. So kinetic energy is very simple. I can assume this distance is basically x from the origin, and this distance is basically y from origin. So kinetic energy is nothing but half m x dot square plus half m y dot square, because it is also given that mass of these two particles are same. So we can write the kinetic energy matrix. So kinetic energy matrix have four elements. So this first element is T11, that is del square T upon del x dot square, that is value of m. Obviously we have to find it at the equilibrium point, but here it will be just a constant value, so there is not any need for that. Similarly, del square T, or just T12 is del square T, del x dot, del y dot, this is also del 21. This is 0 because there is not any mixed term, and there is term T22, del square T, del y dot square, that is m. So we have find the kinetic energy, and this is nothing but the diagonal matrix between, and the diagonal term is obviously mass of the particle. So it's a very trivial, we can easily calculate it. Now the actual challenge is writing the potential energy, then we have to write the potential energy matrix. So what is potential energy? So in this spring, there are the stored potential, and this will be half m x minus L, sorry, half k x minus L whole square. K is the spring constant, L is the natural length, so extension is x minus L. And similarly, for the y, we can also go for half k y minus L whole square. And then we have to also talk about this spring. So obviously, x square plus y square is the total length of this spring, but we have to talk about extension. So natural length is given as √2L. So this value is given as half k dash x square plus y square is the length, but the extension is we have to subtract from √2L, and we have to go for this. So this is my potential energy matrix. The real challenge in this problem is that we have to write potential energy matrix. So this is expression of potential energy. So potential energy matrix have four basic component or four elements. So V11 is del square V upon del x square at the point x is equal to L and y is equal to L, because x is equal to L and y is equal to L is the equilibrium point in this problem. So this is one of the very fundamental thing we have to understand. So if we are going to calculate this value, then this value I have calculated myself. So that is k plus k dash by 2. Similarly, we can write V22. This is just if you are replacing x to y, there is not anything going to change. So this is just a symmetric value, symmetric to x and y in under exchange of coordinate. So del square V upon del y square at the point x is equal to L, y is equal to L, this will be again same value. Now we have to calculate the off diagonal term. So off diagonal term is V12 is equal to V21, because we know this value, this is V is always a symmetric matrix. So del square V, del X, del Y, and this value is nothing. You can at the point, obviously, X is equal to L and Y is equal to L. So these are the equilibrium point. X is equal to L and Y is equal to L is the equilibrium point, and we can calculate V12 is equal to V21, that is basically K dash by 2. So if I am not doing any wrong calculation, then obviously this will be the of all the calculation. You can check it with yourself. Now, according to all this calculation, we have to now write the potential energy matrix. The potential energy matrix is basically K plus K dash by 2. Here is K dash by 2, K dash by 2, K plus K dash by 2. So this is my potential energy matrix. We have my kinetic energy matrix. We have potential energy matrix. Then we have to go for secular equation. So this is V minus omega square T must be equal to 0. And then we can find this value as K plus K dash by 2 minus omega square M, K dash by 2, K dash by 2, K plus K dash by 2 minus omega square M. The determinant of this must be equal to 0. So this is a very simple determinant, just a symmetric thing. So we have, if we are just going to open it, then we have basically K plus K dash by 2 minus omega square M whole square minus this K dash by 2 whole square must be equal to 0. We can use the concept of A square minus B square is equal to A plus B into A minus B. So from here, we can find the value of omega, and that value of omega 1, you can get that is nothing but K upon M, and omega 2 is nothing but K plus K dash upon M. And this is my fundamental frequency, and this is my first overtone. So there are two normal frequency, one is fundamental and second is first overtone. So this is a wonderful problem, and there are a lot of calculation and concept are involved. I especially thank to my team member Mukadder on to solving this problem. He just helped me to calculate all these number, and he also recognized that this X is equal to L and Y is equal to L is the actually equilibrium point. Okay, so this is very interesting that you have to first identify equilibrium point, then you have to go for writing the potential energy matrix. Thank you. Just try to do this problem with yourself.